After Albert Einstein first predicted, in 1916, the existence of gravitational waves caused by the colliding of two massive objects in space, black holes, neutron stars, or from the explosion of supernovae, he dropped the idea completely because he said they were so faint, so exquisitely imperceptible, it would be impossible to ever measure and detect them. And that's where things stood for half a century, until physicists in the West and the Soviet Union began to envision experiments that might measure waves smaller than the nucleus of an atom. Joseph Weber thought they would ring his great bar like a bell, and a young professor at MIT, Ray Weiss, conceived of an instrument that used light and mirrors to measure the inconceivably small warping of space and time that Einstein predicted would be the footprint of a gravitational wave.
The first people to have the idea for a laser interferometer gravity wave detector were two young Russians, Michael Gertzenstein and Vladislav Pustovoit. They published a paper that was not noticed in the West. Ray Weiss, completely independently, had the basic idea. This is around the late 1960s now.
The idea of Ligo came to me in a course where I was trying to explain to the students general relativity, and I barely knew anything. I mean, they knew more than I did in most of the course. There was a revolution going on in the whole idea of gravitation in the early 60s, and I wanted to be part of it. And because I had spent time at Princeton, they thought I knew something about general relativity, which was absurd. The trouble was I couldn't admit to the guy who asked me to teach general relativity here at MIT that I didn't know anything about it. I mean, I came to MIT with this whole big program of doing things in gravity, and then to admit that I didn't know what the hell the theory was about was probably more than I should have admitted, right? So I was one day ahead of the students, or in many cases, just about equal with the students. So it was an interesting term, let me tell you. And I learned a lot. What was the significant thing that I did was something a little different. I was trying to explain gravitational waves. I gave this a problem to the students in the class. I said, how about using light, measuring the motion of objects between geodesics? I mean, everybody got the problem. The mathematics is trivial, it turns out. It's not a hard problem. Otherwise, I would have never been able to do it myself. And that was what I taught in that course. It's the one thing I really began to understand. And I realized in the process of doing that you could make a detector that way.
The most important thing, and the thing that, to me, makes me very firmly identify Ray Weiss as the primary inventor of this, is that Ray did an analysis of all the noise sources that such a gravity wave detector would have to deal with, basically created a blueprint for the future, but it is probably the most powerful paper of its sort that I've ever read in terms of a vision for the future. And this is 1972, after he's been thinking about this for a few years.
What then happened was sort of an interesting thing. I was at that time deeply connected with NASA because I was doing ballooning for the cosmic background radiation and stuff like that. So they asked me to run a committee in 1975 to look at what the space program could do for gravitation and what at that time was called experimental relativity. Kip Thorne, who I'd never met before, came to tell us about what he was interested in experimental gravitation. I picked him up in the middle of the summer. This was in Washington. I don't know if you ever go to Washington, you realize that you can't find any place to stay in the middle of the summer. So he and I spent an evening and a night together in one motel room, and we talked all night. And I mean, literally all night. And what was Kip up to at that time? Kip had probably, as far as I was concerned, the premier group in the world on general relativity. If you look at the names of the people that were in Kip's group, they now illuminate the whole field. A spectacular group that he had put together. He had not heard of interferometric detection of gravitational waves. It was new to him.
I was very skeptical because I didn't really understand at all how this was going to be done to reach the levels of sensitivity that we needed. You're trying to make a measurement of the motion of a mirror at a level of accuracy that is 1/10 billionth the wavelength of light.
10^21 was the number which we designed Ligo for, which means a change in length between the two mirrors, okay? It's a frightening number.
People looked at that and they thought, this is ridiculous. And I looked at that when I first heard about it, and I thought it was so ridiculous that I wrote a little sentence in a textbook, a classic textbook that I co-authored called Gravitation with Charlie Misner and Johnny Wheeler, which said, it seems unlikely that this is ever going to work. And then I spent much of the rest of my career trying to help the experimenters make it work. Because I looked in depth at Ray's analysis of 1972, and I saw it is feasible, but it's going to be extremely difficult. The estimate was that we had in 1978 was 10 to the minus 21 would be where pay dirt is. The gravitational waves that were discovered, the announcement made precisely 1 month ago, the strength of those waves was 10 to the minus 21. It was right on the money. We even had T-shirts at this conference where we agreed on what is our goal, 10 to the minus 21 or bust. This is 1978. 78, that's basically 40 years ago. 78, 88, 98. That's the only way I can do math. 40 years ago. Okay.
The book that Thorne, Misner, and Wheeler wrote, Gravitation, has been the Bible of gravity wave science even longer. It first came out in 1973. John Wheeler had helped launch the search for gravitational waves among his many pioneering achievements. But it was a different, more primitive technology than Ray and Kip talked about that night. It was called a resonant bar detector, and its most famous experimenter, Joseph Weber, would become both one of the most famous physicists of the late 1960s and early 70s, and then a pariah among his physics colleagues.
You'll get different opinions on this, but my opinion is that without Joe Weber, we wouldn't be here. There would have been no gravitational. Nobody would have done anything as mad as tried to detect gravitational waves with terrestrial detectors. It's basically impossible.
So this is an artifact. It's one of the bars that Joe Weber used in the 1960s. Joe was the first person to take seriously as an experimentalist to try to actually make a detection of gravity waves. And so what we have here is a very large aluminum bar which is suspended, so you can actually see it moving. The theory was that if a gravity wave comes by and space expands and contracts, that energy would be released as a sound wave in the bar. Joe was a controversial character, and people don't give a lot of credence to his claims that he had actually detected gravitational waves. But to me, Joe is a hero because even though he's a model of what not to do in data analysis, he was the person who had the chutzpah to go and make this first attempt. If it wasn't for that pioneering work, we might well not be here, and he did think of many of the ideas that we would later incorporate into our practice.
The laser interferometers really started in the early 70s, and there were developments in many places in the world. The first real prototype of a gravitational wave detector was laser interferometers, suspended mirrors, and all the major parts was built in Munich by the Max Planck Group. My predecessor in my Max Planck job, Heinz Billing, was one of the first 1, 2, 3 people who actually tried to experimentally detect gravitational waves half a century ago.
Heinz Billing was already famous in Europe for having designed the first magnetic storage system for computers. And then, in 1952, building Germany's first electronic computer. Billing got involved in gravitational wave detection when he was asked to test Joe Weber's claims in the US.
That's what he did. He said, I will copy the Weber cylinder just as closely as is possible.
At the same time, at the University of Glasgow in Scotland, Jim Huff and Ron Drever also built and tested a bar detector.
And with all of this effort, no gravitational waves were detected. So the outcome was, of course, clear. Something needs to be done to make these detectors more sensitive. And Billing said, why not try what Ray Weiss is proposing at MIT.
Rudiger was the last senior member of the German group that was so important in developing the techniques. They made the first really, I would say, well-tested prototypes.
So what happened, I'll tell you what interesting happened. They, the German group, took that whole idea and ran with it. And with my blessing, by the way. Billings, who was the head of the group, calls me up and says, have you got any graduate students who are working on this very good idea you have? And I couldn't believe it. But then I said, well, at the time, I don't have any graduate students working on it because there's no money for it. Well, is there anybody? And it turns out later on, there's David Shoemaker, an exquisite experimenter. I mean, superb experimenter. David went to Europe and actually worked with the Germans.
I had been working here in the lab with Ray and colleagues on a small gravitational wave interferometer in the early 80s.
It was clear that he really grasped all the technical details very quickly and so made his very good contributions due to his ingenuity and due to his youth.
Honestly, they were a little bit tired working together. They'd been working so long on these projects that they just lost a bit of the spark. And I was the ingredient that they needed. I knew nothing. I was full of questions and I was full of energy. And I was able to just fall into the group. So I often found myself working all alone on weekends. The Germans were not working on weekends. And would surprise them on Monday morning with a bunch of findings that I couldn't explain, and they could.
And he was the guy who actually got them going again. And there's an absolutely wonderful paper that he wrote with all of them. He's the lead author of that paper.
The collection of noise sources that Ray had mapped out in 1972 as a guide, trying to measure each one of those in this instrument, we were able to come up with something that really brought the field forward, I think, in a way, and gave people a lot more confidence that we could build sensitive instruments.
Very important, the German confirmation of these ideas, that they could make a thing work at the theoretical limit. It was really spectacular what they did. I felt confident that you could take it and extrapolate it. I saw nothing that would stand in the way of that, short of money.
In the summer of 1988, Kip Thorne, after a number of years, convinced me to move to Caltech to take on this type of research.
Kip was an extraordinary popularizer. He would go around and grab everybody and beat them over the head and point out to them that this was such an important problem. It was, you know, like going to a revival meeting with this incredible preacher throwing fire and brimstone at you. And you had to go away convinced that this was really worthwhile and exciting and hard.
We took a lot of great work that had been done long before I joined and used that understanding to write the construction proposal, to build this big, gigantic, monumental thing. And we faced all the problems of, you know, trying to get NSF to bet the farm on this, which is what they did. Very brave people took this on, a project that was, you know, 10 times bigger than anything NSF had ever done before, very high risk.
The thing that surprised me the most in all of this has been how the National Science Foundation came to support this, to take such a big risk, and then to stick with it.
This proposal, the preface began, requests support for the design and construction of a novel scientific facility, a gravitational wave observatory that will open a new observational window on the universe. It proposed opening a new era in our understanding of the universe, but Ray understood clearly that it also meant a new era for LIGO and its just-born search for gravitational waves. For the past 15 years, he had also been leading another potentially mind-bending cosmic experiment, NASA's Coby Satellite, which in 1992 would stun the world with its historic image of the earliest light in the universe, the cosmic microwave background, a mere 380,000 years after the Big Bang.
I'll tell you what Coby did in one thing, and then I'll let it go at that. It made me less frightened of the transition from small science to big science. I knew that we were in the soup because we were already then talking about $100 million. And I knew that $100 million was an amount that was unheard of. You would have to have a group that did this and whole structure that was associated with it. And that was an anathema to most of us who had sort of a lab with one table, a couple of tables in it, and dealing with graduate students every day. And that transition was an experience that Coby taught me, and it taught me that you could get around it if you maintained your head. In other words, if you didn't get sleepless nights every time you ran into a dumb thing, okay, you just roll with it, okay?
The 1989 proposal was written by Robbie Vogt, who had been a provost of Caltech and came on as the LIGO project director. He was joined by Kip, Ray, Fred Robb, and Ron Drever, who had been a leader of the important Glasgow Gravitational Wave Group and had come to Caltech to join Kip and Ray as one of the founders of LIGO.
We wrote a proposal, which I think is a magnificent proposal, in 1989 under Robbie's tutelage, which got us effectively into the business of a large project. And then what happened was that there was a significant falling out between Ron Drever and Robbie Vogt, which is most unfortunate. So what happened is that caused all sorts of hell to break out loose. It was in every newspaper that this terrible thing had happened to the LIGO project. It got busted up.
The director of the NSF informed the Congress that they were interrupting the funding for the project, which is a very serious act. And they told the Caltech that the leadership of LIGO needed to be changed. So Barry was asked to be the new director of LIGO.
Barry was an absolute breath of fresh air in the sense that he had been through it. He'd been through the SSC. He knew how to run a big project. He knew how to deal with people. He just knew exactly what he needed, and he hired people to do it, and little by little, the thing took on the feeling of a real project.
I think it's quite clear that if Barry hadn't come along and brought his talents and skills to LIGO, it would have crashed and burned. We were in a crisis. Not the first crisis. I lived through about 4 or 5 of them, but one that would have been the final fatal one. We were approved in 1994 to build LIGO, and it took 5 years to do the physical building, which was maybe only a year longer than I thought. It took 5 years to make it work, which is 5 years longer than I thought. Really, because it's very, very difficult and there was no precedent.
At that time, we knew that the technology that existed would have to be invented.
There really are no experts you can ask, how do you do this? Or if you ask people who, seem to be experts, they give you completely, different ideas about what you should do.
In order to detect gravitational waves, we had to push technology so far that the risks of not succeeding right away were great enough that we didn't have the nerve to try to sell the whole thing at the beginning. And I don't even think the NSF, which is the only funding agency that would fund this thing anyway, would have taken it on. So what we proposed was to build a first phase of LIGO that had the whole infrastructure for the eventual LIGO and had all the techniques that you need and sensitivity enough to take it seriously. Sensitive enough so detection of gravitational waves was possible. So the key word was possible. And it's really what was behind us doing it in 2 stages too, is not just the risk in selling it, but the risk in ourselves learning how to do it and doing it.
Initial LIGO launched in 2002. One of the great breakthroughs in its instrumentation was made by Ray's graduate student, Nergis Malvavala, and Barry's grad student, Matt Evans.
Well, just Nergis is quite something. She did as a thesis, I think, one of the more important theses that was done here. Namely, she showed how you could use an idea that's been around but nobody had ever really made work. How you could align the interferometer. It's one of the more troublesome and difficult parts of the whole interferometer is that automatic alignment system.
So the problem of alignment in initial LIGO was that you have these 2 mirrors that are 4 kilometers apart, and you have to make them face each other with a tolerance of 10 nanoradians. Otherwise, the interferometer wouldn't work the way it's supposed to. So that was the challenge. Eventually, the way that we ended up solving this problem is the only thing that really talks to both mirrors is the light beam itself. So we understood that we had to use the laser beam to carry information about the angles of the mirrors. And we were already using the laser beams to give us information about the length of the separation. So we added another measurement, if you will, where normally you take a laser beam and you just measure all the power across the whole beam, just integrate over the whole thing. And we understood that if the mirrors were misaligned, the power wouldn't be distributed uniformly. It would have lobes of they're called modes. It would have different amounts of power in this quarter than that quarter. And so we actually measured different amounts of power across the beam, and that was, told us what the alignment was. So that was the solution.
And then she got a postdoc at Caltech, and she did a lot of things there, among them training Matt Evans. Matt Evans she wasn't a professor yet, but effectively Matt was her student. And they then did something spectacular on their own. They learned how to do something which none of us knew how to do. Namely, they got the interferometer at Hanford. They learned how to get it aligned because of her early work, but then also to get it into position so that it became sensitive. And what does that mean? That means you have to get the mirrors in the right place, exactly the right place, within much, much less than the size of the wavelength of light, positioned properly so that all of a sudden the entire interferometer lights up. That's called locking the interferometer. And that was a relief for the entire project because it had never been done before.
That was the kind of first light in the interferometer, and it was a very exciting time for me because it was my thesis work, but I think also for other people. It was a great time because it was the first time we had seen really the interferometer operating in the way that it ought to.